Hey everyone, welcome to the first videos from Chapter 7. So you'll notice the number system is a little bit different. That's because I'm not quite exactly following the sections of the book for this chapter. I'm kind of following, but not quite exactly. I'm going to kind of jumping around between them. So it'll be a lot easier I'm just doing a set of videos for day 1, a set of videos for day 2. It'll be easier to sort out that way. So we're switching gears a lot going into Chapter 7. Chapter 3 we talked about second order ODEs. And now in chapter 7, we're talking a lot about systems. So systems are a different sort of beast overall. And we're going to sort of figure out what they are, talk about them a little more in this video. And the next videos we'll talk about more how we can go through solving them and the tools we need to try to solve them. So they are systems, which means you do need a little bit of linear algebra to solve them. But I'll be going through that in the next couple of videos, the parts of linear algebra that you need to actually be able to handle this stuff. So in this video, we're just talking about systems in general, what they are, how they come to be, and then sort of how to formulate them. Let's go ahead and start talking about systems. So the first main question to ask about this is obviously what are they? What are systems of ODEs? So the thing, we talked about this at the very beginning of the course, the thing that distinguishes a system of ODEs from just an ODE itself is that systems of ODEs have multiple dependent variables, all of which depend on a single independent variable, which we're going to denote by t, and usually refers to time. So systems have multiple dependent variables, which basically means multiple equations to solve for, but they all only depend on one independent variable, which you're trying to think of as time. So the notation we'll use for this stuff, at least the general notation, it might change a little bit when we get to certain problems, but for the general notation, we'll have x1, x2, up to xn being our dependent variables or our unknown functions, and t will be our independent variable or time. So the first question you could ask is, where could these systems come from? How do we get systems like this coming up in natural situations? So how do we get systems? Well, there are two main ways. The first is by modeling multiple things at the same time. And the kind of easiest example of this is the two masses in springs sort of setup. So you have this sort of a picture here, and you want to write equations to govern x1 and x2, the positions of the two masses as time goes on. Now the key thing about systems is, in general, your two equations will depend on each other. So for instance, in this case, you get something that looks like this. Mass second derivative x1 in time is negative k1 x1, so that's the spring force from this first spring, plus a k2 times x2 minus x1, plus whatever external forcing you have. And for mass 2, you get a minus k2 x2 minus x1, minus a k3 x2, plus your forcing on the second one. So if x1 and x2 didn't depend on each other, you could solve them both individually and just go from there. But in this case, they do depend on each other through this k2 term that shows up in both equations. So you have to solve them sort of at the same time because they interplay with each other. And that's the main thing that you get out of systems, that the equations aren't all independent. They are all linked together. And you have to solve them all simultaneously to get a solution instead of solving them all one at a time. Now the second way we can get systems is by reducing a higher order equation into a system of equations. So let's take a look at an example where we're trying to solve the ODE yn equals some function f of t, y, y prime, y, n minus 1. So some nth order ODE. What we can do is we can set x1 to be y, x2 to be y prime, on down to xn to be the nth minus 1 derivative of y. And then I can use all of this information to make a system of equations, where what is the derivative of x1? Well, the derivative of x1 is going to be y prime, which is x2. The derivative of x2 is going to be y double prime, which is going to be x3. And the derivative of xn is going to be yn, which, if I know what yn is from this equation up here, this is just f of t x1 up through xn. So this gives me a way to convert a higher order equation into a system of equations. So if I have an nth order ODE, I can convert that into an n by n, or an nth order system, or an n function system, however you want to talk about it. Yeah, n function systems. These are all first order systems because they only involve one derivative of my function, but they are n function systems. So throughout this section, we're only considering first order systems. We might get second order systems like the one above for the mass spring system en route to solving them. But when we solve it, we reduce that to a first order system, which in the case of the masses and springs would involve 4 component functions. So what does the general first order system look like? Well, the general first order system is something like x1 prime equals f1 of t x1 through xn, x2 prime equals f2 of t x1 up to xn, and xn prime equals fn of t x1 up to xn. This is our general first order system, and it only involves first order derivatives of each of the functions, and we assume we can put those on the left-hand side, and then we just get expressions in terms of all the functions on the right. Now, what do we mean by a solution to a system? A solution to the above system is n functions, phi1, phi2, up through phi(n), such that phi1 prime equals f1 of t phi1 phi(n), and similarly for all other equations, there are n of them, for all t on some interval. So this is a solution on an interval, then this solves this for all t on some interval, which means if you're going to check this, you literally just have to plug in, but you have to leave everything as a function of t until you're done, until you verify that it's all equal. And initial conditions are given in the following form. Initial conditions look like x1 of t0 equals x10, x2 of t0 equals x20, xn of t0 equals xn0. So for initial conditions, we specify all the functions' values at one point, as generally we always do for these. For the higher order equation for second order equations, in chapter 3, we specified a function and its derivative at the point. Here we need to specify n conditions as well, but it's just all the values of the n functions at a certain point. And then we also, as are in the first section of the book for this chapter, we also have existence and uniqueness theorems for this stuff, which should look very similar to ones that you've seen before for the second order and first order equations. But we'll come back to those and talk about them later once we start figuring out what we actually need to figure out how to handle these and try to solve them. So those are the main points of this video. Basically, what are systems and what does the general first order system look like? In the next video, we'll specify to what linear systems look like and sort of start figuring out the tools that we need to be more consistent in how we write them and trying to solve them. All right, that's the point for this video. Thanks a lot for watching, and I'll see you in the next one where we start talking about linear systems.